turn on as usual. Does it work? Yes, it should. All right, so today we have to talk, or we should talk about the previous theoretical exercise, which I had to postpone to this week, and a bit about the practical exercise. So I was a bit surprised that there was actually no single hand in for theoretical exercise 4. I know it's optional, so you don't have to, but of course you can get feedback if you want. So in the first question for theoretical exercise 4, you were asked to construct a deck, so a directed acyclic graph, so a graph actually containing sort of an optimized representation of your program. And so I thought it would be a good idea to just repeat what deck construction actually is all about. So in such a deck, interior nodes always represent the operators of an expression, and in turn the exterior nodes, or just the leaf nodes, which have no child nodes, always represent, well, whatever is the rest of the expression, so a name for a variable or an identifier or a numeric constant. And when you construct such a deck, you should check to make sure that if there's a node with the same value, that you can reuse it. So that's the idea behind optimization, obviously. And you only need to create a new node when there's no node with the same value around. And this helps in detecting the common subexpressions and avoiding recomputing an expression or a partial expression you have recomputed already. And assignment instructions are only performed when they're necessary. So these are 3 simple rules. So let's take a look at some what's going on here. Let's add some examples. So this is not an example from the exercise sheet, but just a general example. So we have expressions here, a plus b multiplied with a plus b plus c, and both sums have to be evaluated first because they're in brackets. And what we can do is we can write 3 address code for this. So we could calculate a plus b first, assign it to a temporary variable t1. Then we could, since we already have a plus b, calculate a plus b plus c. So since we already have a plus b in t1, we can reuse that intermediate result and calculate t1 plus c and assign this to a second intermediate variable t2. So we have our both of our sums here as terms in t1 and t2. And then finally, we can calculate the product of both. So we have t1 and t2 already storing the intermediate results, and we can store this in t3. So that's what we observed. This common subexpression a plus b has already been expressed in a single node in the deck, and the computation needs to be carried out only once because we're not changing the value of the variable afterwards. And if you draw such a deck, and I've annotated the intermediate results, so where the intermediate results of the operations are stored, you have a plus b, which is stored in t1, and this is used in t2, which adds this intermediate result to c, and then the intermediate results t1 and t2 obtained by the 2 additions here are then finally multiplied to give t3. A bit more of a complex example is that one here. So we only have one variable here, a, and so we're always reusing expressions involving a. So we have a plus a plus a plus a plus the same again, and of course with the brackets as shown on the slide. So essentially we need to make sure we only have one instance of a here, and then we're reusing it to evaluate this inner expression here. So this plus operator here with 2 links to a represents a plus a, and then we can reuse this. So we can then have an expression for the left and right sums, which are identical. So that would be this plus operator, which would in both cases refer to our inner sum a plus a here. And then finally, we have our plus in the middle, summing up the total, which has the identical expression on the left-hand and right-hand side. So we can refer in both cases to that intermediate sum here. Now that's of course an extreme case, but as you can imagine, like we would have 1, 2, 3, 4, 5, 6, 7 additions here in the original case. And now we could reduce it to only variable references and doing 3 additions. So code generated from this, well, I think it's easy to see that this would execute faster. So let's look at some real-world examples from the exercise sheet. So we gave some simple expressions, and the assumption is that the plus operator is left associative. What does left associative mean? It means that if we have operators of the same precedence, they are evaluated in order from left to right. So we're taking the first operator first. So in evaluating that expression, we first calculate a plus b, and then we would add the intermediate sum of a plus b to the rest. And we need to evaluate the rest separately because it's in brackets, so it doesn't have the same precedence here. So if we write 3 address code for this, we would first generate an intermediate result for a plus b. Well, then we would maybe generate another intermediate result, a plus b for that one here, and you can already see this is redundant. And then we would write T3 equals T1 plus T2. A regular est, so a parse tree, would look like that here. So we have the sum on the left and right hand side, and then we add the intermediate sums together here. So obviously we can eliminate one of these a plus b sums here because we already have the intermediate result. And so our DAG for a plus b, calculated down here, a plus b again, already obtained here, looks like this. And then we can add the 2 intermediate sums together to form our final result. All right. Now, the next equation looked pretty similar. So what's the difference here? So the difference is that this is left associative. So when we want to calculate it using left association, we first need to calculate a plus b as before. And then we need to add the sum of a plus b to a because we're always evaluating from left to right. And finally, we would add the intermediate sum here to b. So this is a different order of evaluation, which means that when we write 3 address code, well, we first calculate the left-hand side a plus b here. Then we add the second a to our intermediate result here, and that's what's different here. And then finally, to this second intermediate result, a plus b plus a, we add our final b down here. And so our DAG looks different. So we're still reusing a plus b, but now our intermediate expressions look a bit different here. So essentially, this is the consequence of actually having this different order of evaluation now here, enforced by this left associativity. And finally, we had this more complex expression here. So just a lot of a's summed together with some precedence operators here. And we could write 3 address code like this. So we start evaluating from the left. So a plus a gives our first intermediate result. So this is our green plus sign here. Then we need to evaluate the outer brackets here. So a plus a plus a. Again, since we only have 2 operators, we would calculate a plus a here, which we already have calculated. So we can reuse the intermediate result in T1. And then we would just add a to that intermediate result. And then we can add the inner bracket here. So this again is a plus a, which is T3 again, plus another a. And then finally, we can add these 2 partial sums in the brackets together using our red plus sign. So we add our intermediate results T3 here and T6 to give a new variable T7, which has the sum of everything that's in the brackets here. And then finally, we can add this together with the left intermediate result in T1. And since we're only allowed to reuse things, we have our a down here, and a is referenced quite a number of times here already. And you see all the arrows here indicate where reuse of expressions actually takes place. And you see the number of addition operations we have to perform here is reduced compared to the original. I think that's relatively simple. So I hope there were no major problems with this. All right. So the next question was, again, expression translation into syntax trees and quadruples in this case for our 3-address code intermediate representation as that we used in the lecture here. So first we had some array accesses. So we accessed an array B and its element I, and then element J of array C. So what we do here, we have these array operators here. So accessing an array of an element of an array, which would refer to a base array at the index of the element for C and B. Then we can sum this together. And finally, we have the assignment operator assigning this to A. And we can write it like this in our operation. So we don't need to break it down into pointers and offset calculations as you would do when you would write it in machine code. But our intermediate code is on a bit of a higher representation because exactly which machine address this is actually dependent, for example, on the size of a pointer and so on. So essentially, we're just loading our first intermediate variable from array B, then our second one from array C. Then we add it together in a third temporary variable, which we finally assign to our output variable here. Well, in B, it wasn't much more complicated. The only thing we had now was an assignment to an array element on the left-hand side. So here we would just need to build our syntax tree for B times C, then B times D. Then we need to subtract the one product here from the other and assign it to our array element A of I, which we construct as we've seen on the previous slide. And finally, we have some function calls. So function call is essentially just a name and a list of parameters. And this list of parameters, like in C, can be an expression. So if we call f of y plus 1, we first need to evaluate y plus 1. Then we call f. F is a function that we assume to deliver a result because we add this result then to our constant 2. So we have our y plus 1, our intermediate, well, inner expression here for our parameter, which we evaluate. Then we do a function call of f, and this function call returns a value like an integer, for example. We add this to our constant 2, and we assign it to x. So here we have used these param shortcuts in our intermediate representation, and these might later on translate to something like pushing this variable on the stack or loading it into a specific register, depending on your application binary interface that is specified for function calls. So this differs depending on your specific CPU and the ABI used by that CPU. So this means we should be able to abstract from this in our intermediate representation to be able to translate it accordingly when we generate real machine code later. And the same for call. So which call instruction is actually used depends on the CPU you're going to use. And then we had another expression which involved pointers here. So x equals the contents of P, so PD reference plus the address of Y. And here you see, since this is also machine dependent, which machine instructions would actually be generated. So if you can, for example, access a memory location in an instruction, in an arithmetic instruction directly, or if you have to load it first. So here we keep our abstract level and say, okay, we dereference our pointer P, load it into T1, the dereferenced value, we get the address of variable Y, load it in T2, then we add them together, which obviously would mean that your language would allow to add pointer values together. This works in C. Other languages don't allow this for general pointers. And finally, we assign this to X. So we have no data types, so we're on a very abstract level here. We've already had a quick look at LLVM intermediate representation where data types are preserved. So in LLVM intermediate representation, for example, this expression or the intermediate representation code for this expression would look a bit more complex. Finally, we had a question on basic blocks and 3-address code analysis. So the first question was really to figure out from our 3-address code where our basic blocks start and end. And as we know, our basic blocks always end when there's a change of control flow or a possible change of control flow. So if we have a conditional or unconditional jump. That's the last instruction in the basic block. And the first instruction in the basic block is usually an instruction we can jump to. So, well, we start with a simple one. Of course, B1 starts at the beginning. It has two input values that are assigned, so there's no change of control flow. So this is B1. Now, what you need to do is you need to check all the branch targets. So essentially what we would do in the next question, we would need to build a control flow graph. And we see, for example, here down in line 15, we have a conditional jump. If the condition C is less than D is fulfilled, we jump to line 3. Since we can now enter this line of code here in line 3 from above, so from B1, or from below here, we need to start a new basic block because control flow can change here. So inside of that basic block, we have 3 arithmetic expressions with assignments. Those don't change the control flow. And finally, we have another conditional jump. If A is less than C, go to line 8. So our basic block has to end here. Accordingly, a new one has to start. This new basic block now only consists of the expression on line 7 because line 8 again is a branch target. So we have a new basic block starting here already. So then we have another set of assignments and a conditional jump here. So if dt2 equals to 0, we jump again to line 17. So our fourth basic block ends at line 11. Accordingly, the next one starts at line 12. And this goes until line 15. So we have another condition here, which would include a jump. So we have a new basic block here. And since line 17 is a branch target from above here, this sixth basic block only consists of this one single instruction here. And then finally, we have our seventh basic block down here. So figuring out basic blocks is relatively simple. The only thing you need to take care of is not to ignore any branch target for some conditional or unconditional branch, because this means that you have to start a new basic block on the line of the target. And well, if you have already drawn these arrows here, it's very simple to change this to a control flow graph, which, well, is no big surprise. Looks pretty similar. So what you usually do is for more complex programs, you don't really write all the instructions making up the basic blocks in your control flow graph, but only note the basic blocks, and then you can write down the basic blocks somewhere else. This makes this diagram a bit easier to understand. And here you see we have something like a loop actually. So B2, B4, B5 would cause a loop. Whereas in B4, we could also decide to terminate the loop, and we could also terminate our loop in B5 and then have an additional instruction adding A plus B to give C down here. So an interesting question which we didn't ask is try to translate this back to C code to see what this would look like. That's actually an interesting question. We should have included this. Okay. And then we had our practical exercise 4. So this was all about simplifying trees. So I think all of you have more or less managed that. So I'll not present any example code because this is boring pointer handling. So we'll go through it and give you appropriate comments to your solutions that are handed in, because they might depend on your specific version or way of building the tree and constructing things and doing the recursion. So a general solution here won't be of much help. So I'm just giving a global overview of what we could have done here, or you could have done here. So what needs to be done for this, or needed to be done, was to do a recursive traversal of the syntax tree that you constructed early on using your YAK parser. And this is comparatively simple, except for, of course, all kinds of pointers involved. There's less typing than with the previous example. The remaining 2 exercises will maybe be a bit more work again, at least considering the amount of typing. Now, so the results and how easy it is to work with this really depends on how comfortable you are with using recursion. And some of you feel that recursion is pretty natural, and some of you seem to struggle with it. So recursion obviously is, if you have an arbitrary tree as an input, is a very useful approach to walk through that tree. So to traverse that tree. And essentially what we're doing now for optimizations for simplifying trees is just walk this tree up and down and potentially changing it when we find some certain conditions. So that was probably a good idea to see how this tree recursion works. And I think it's not that complicated. So we have seen that when we construct our abstract syntax tree, that we have some nodes that are just there because our grammar was easier to write that way. And so we have some sort of intermediate node here that leads to a different node in the same hierarchy here, and only that node here has two child nodes here. So for generating code, we don't need this intermediate node any longer here. So what we can do is, if we have a structure like this, we have a grandparent, a parent node, then a child node of that parent node, and this child node has two, well, grandchildren, if we would say this, of its own. Then we could just remove this parent node, we could kick it out, and we have to reroute the pointer from the child to the grandparent directly, which is what we did on the right-hand side. And then we can remove the parent here from our tree, so we'd save a bit of memory for this. So this is part A, just removing syntax artifacts. Now, another thing that could happen is that your tree might look like this. So you have some sort of parent for a single child node, which refers to another parent of the same type with another child node, and so on and so forth. If you wanted to traverse this tree, you'd have to go through all of these. But since these are usually the result of parsing on the same level of, for example, an expression, we'd only need this one here. So you would just need to know it's one parent node of type L, and then 4 child nodes just attached to that parent node. So what you could do is you can try to flatten the tree here. That's what we wanted in parse B here, actually. So to remove all these redundant L nodes here and to attach all these child nodes here to a single parent node here. Because, well, it saves a lot of work because it saves you a number of iterations going through all of these if you want to, for example, visit all the child nodes here. So here you only have to go one level deeper. So what you do is you recur to the bottom here first. So you start here and go down here and here until you find that this L only has one child node here. So no more L on the right-hand side here. And then what you do is you recursively again remove this L node. So as we've seen with the redundant node before, so you just remove it, attach L's child node to the L one level above, and you can kick that one out here. And of course, you can repeat this again. So you have, well, removed one more L and so on until you only have one L left with all 4 child nodes attached. And finally, we can use things like these for expressions. So for these, we would have to do some calculations and not just remove nodes. But if you recur to the bottom node first, or to the bottom nodes, and then handle the rewriting when you walk up the tree again, then you can actually reduce the tree or the expressions in the tree. So you would add some semantics to this. So when you find out you have an expression node consisting just of an operator multiplication, for example, and this operator has 2 child nodes, which are both constants here, then you know you can replace the whole subtree here, so 2 times 8, obviously, with the result of multiplying 2 times 8 at compile time. So you could replace this whole subtree here by a single child node with a value of 16. And then you can go up the tree again. You figure out now your minus operator node only has 2 constant child nodes again. So you can do this replacement once more. So you can calculate 16 minus 7. So you would reduce this, well, not large, but this tree here, at least this expression tree, to a single constant 9, which then, well, can be used in your program wherever, such this exact subtree shows up. And of course, since you don't have to do the multiplication and subtraction at runtime anymore, because you did it once at compile time, your program already got a bit faster. So this was all a bit more difficult when you had trouble really getting the recursion to work in your tree. But otherwise, I think that wasn't, excuse me, and that wasn't too difficult. So that was what that was all about. So in the next practical exercise, PE5, which is coming out, well, this evening, I think, I'll just have to do some reformatting and checking if all the source code we have is really compiling and works. The next task is to build a symbol table. So whenever a variable is declared or variable is used, we need to know in which places it actually shows up, so we can well, assign a memory location for it or register later on. So our next part of the compiler building, part of building the compiler is actually to create a symbol table for the symbols in our VSL program. And then finally, in our last task, so after Easter, we will finish generating the compiler or building our compiler by really generating x86 machine code. For this, I'll have to work out a bit of a trick because some of you are using Macs and the assembler format on the Mac is different. So I need to experiment a bit to get this to work, so we have the same output format that can be generated by the compiler on Mac and Intel, so you don't have any trouble just porting your code over, or yeah, we don't have to check for different conditions here. So essentially what we expect your compiler to do in the end is to output assembler source code instead of binary code that's linkable, because that makes it easier. You just need the right assembler that understands this variant of x86 assembler. And as you've seen in the assembler lecture, there's different variables of variants of x86 assembler, and we need to choose the correct one, obviously, because otherwise our assembler will complain. And then finally, our system linker will take care of the linking. So well, that would be a lot of work to also implement the rest. So we'll stop here at generating assembly code and let the system tools do the rest of the work. So that's all from my side for today. I'll stop sharing and stop recording.